In this video, I will explain the Castigliano theorem. Here we have a body. Let's start from the general shape of a body. It's about strength of materials. It's a subject of strength of materials. So deformable bodies are the subject of strength of materials. So there are P1, P2, P3 and n number of forces, concentrated forces acting on the body. And in the direction of these concentrated forces, there are delta 1, delta 2, delta 3 and delta n number of displacements occur in the body. There are displacements, but also these are the deformations of the body. Actually, let's say displacements of the body. Here, UD is the work done on the body by external forces or the potential energy of external forces. And as we all know, since it's statics, strength of materials is interested in statics, so loads are static loads, which are gradually, slowly applied on the body. So 1/2 factor comes to the energy factor, which are force times the displacement along force. Here P1 delta 1 is multiplied by 1/2. Since loads are static loads, static loads, the value of P1 starts from 0 and reaches to its final value, which is P1 itself. So the average value is 1/2 P1 times the displacement in the direction of P1. And we do this for all forces, and we obtain potential energy of external forces is equation 1. Since in statics conservation of potential energy is valid, the potential energy of internal forces moments is equal to the potential energy of external forces moments. That means, let's say UI is the potential energy of internal forces moments, forces and moments, forces only, moments only, or forces and moments. Since in statics conservation of potential energy is valid again, UI equals to UD. Okay? That means in a conservative system, the potential energy of external forces moments just passes to the internal forces moments, or the potential energy of the internal forces moments. The second Castigliano theorem states that the first derivative of UD with respect to Pj is equal to delta G. That was G.
J.
Sorry, it's J. So the first derivative of potential energy of external forces with respect to P2 equals to delta 2. Okay, J. However, the correctness of equation 3 cannot be shown by using the function of UD. This function. By using this function, one cannot prove that this equation is correct. Because even the P1, P2, P3 till Pn external forces are independent from each other. They are independent from each other. Delta 1 is a function of, or dependent on, sorry, there is a grammatical mistake here. Delta 1 is a function of or dependent on P1, P2, P3, Pn, all forces. Here you see these are independent from each other, P1, P2, P3, but delta 1 is dependent to all P's. Delta 2 is also dependent to all P's. As we all know here, if I remove P2, P3, Pn and other forces, in addition to delta 1, any delta 2, any delta 3, any delta n will occur also in the body because of only that P1 force. So one must obtain the expressions, functions of delta 1, delta 2, delta 3 in terms of all those P forces. To use this formula to apply the second Castigliano theorem. And then if the result is as it is stated here, then we can say that Castigliano is correct. Therefore, the formula must be proved in another way. Assume that J equals 2 and the differential load dP2 is applied in the sense and direction of P2. As a result, a differential displacement d delta 2 occurs in the direction and sense of dP2. An additional load is applied here. Assume that other displacements developed in the directions P1, P2, P3, Pn respectively are small enough in comparison to d delta 2. In this case, those terms are here in UD. New two terms come here. There is an increment. This force is a static applied increment, and this increment occurs also in the body in the direction of this load. So this new term comes. This was here, P2 was here, but its starting value and the final value is same. It's both of them are P2. So the average value is P2. It's again static, but was not increased from 0 to P2. This times it's kept constant. So the constant load is multiplied with the new differential displacement. Okay. Now this is a differential displacement. Anyway, it is applied to the body. No any other displacement is applied to the body. So because of this additional this is an assumption, of course, because of this small load increment, load increments occur in the direction of P1, P2, P3 and other loads, but they are very small. That's why they are neglected in the expression. If UD is subtracted from UD plus DUD, the increment in the potential energy of external forces is obtained as so. Okay, that means that subtract this expression from this expression and we obtain this one. Since this term is very small, this term is also very small, differential, its multiplication can be neglected and can be assumed as 0. So only this term remains in the expression. Okay. This term can also be replaced by another term. I will show it now here. Now, this is the static load P and delta. Since it complies with Hooke's law, displacement increases proportionally or linearly with respect to P. So P2 is increased to P2 plus dP2, and delta 2 is increased proportionally to delta 2 plus d delta 2. And according to Hooke's law, this line is valid. Now, if I divide the area here under sub-areas and refer them as A1, A2, A3, A4, A5, A6. From the geometry of the figure, we can see that A3 is equal to A3 equals to A4. Okay, from here you can understand it. A3 is equals to, these are rectangular areas, dp2 times delta 2. dp2 times difference here. The length here is delta 2. Okay. A4 equals to d delta 2, this length, times p2. Okay. Now you see here, I had here p2 times d delta 2. p2 times d delta 2. So I can replace this term with this term, dp2 times delta 2. I replace it, then the increment in the external potential energy of the potential energy of external loads is equal to this one. So if I from here I obtain the first derivative of the potential energy of external functions with respect to P2 gives me the displacement in the direction of P2, which is delta 2. So according to this result, which is geometrically obtained, the second Castigliano's second theorem is correct. According to equation 7, Castigliano theorem is correct. Similarly, to calculate the rotation in the direction of a moment, use the formula given below. Okay? Make a similar proof and you will easily can obtain that this is also true. However, this theory cannot be used in this way because all deltas embedded in the expression of UD are dependent on all external forces moments. Okay? So we need the function of dud. Mathematically, it cannot be used. Here, using some geometrical shapes and using some symbols, we have proved that it's valid, but to use its specific structural problems, we need that the function of UD is obtained by suitable functions. Since the functions of forces are not known, these functions can be replaced in equation 1. These functions cannot be replaced in equation 1, and the calculation of cannot be, this cannot be calculated, or that one cannot be calculated. Sorry, there is a mistake here. Since the functions of P1, P2, P3, Pn, it should have been delta 1, delta 2, delta 3, delta, and because these functions are not known. Okay, these functions are not. As a result, I will summarize here. UD is a function given here, but deltas functions are not available. Okay, in terms of OPs, so we can't use this. In an example, you will understand what I mean. I have a bit confused here, and I made a mistake here in the paragraph text. I might have made a mistake. Now let's prove the correctness of Castigliano theorem using a simple supported beam given below. Now this simple supported beam is a body which is used in strength of metals and it's subject of civil engineering. And there are three loads applied to it, and you see the displacement in the direction of these forces. The potential energy of the external forces moments given in figure are as follows. Everyone will understand. It's easy, nothing changed. Although the shape of the body changed, potential energy of external forces is same. Now a differential force in the magnitude of dp1 is applied on the structure given in figure 2. dp1 is applied here, and which has reached to equilibrium. The beam reached equilibrium here. The beam was in equilibrium under P1, P2, P3 as you see here. Then a differential load dP1 is added and the beam again reached the equilibrium here in this position, which is shown with dashed line, dashed curve. And the additional displacements are d delta 1, d delta 2, d delta 3 as you see in figure 3. According to figure 3, the increment in the potential energy of external forces is as follows. Now, this is the increment. 1 over 2 dP1 times d delta 2. This is the static load. Its value is increased from 0 to its final value, dP1. That's why the average value is 1 over 2 times dP1. The average value of the static load, dP1, times the increment, distance increment along itself. But P1 was constant here. During this time, the value of P1 did not change. So there is no 1/2 in front of its expression. P1 times d delta 2 comes here. Here, since P2 and P3 were also constants, in front of their expressions, no 1 over 2 term or number comes. Summing up equation 8 and 9, this equation and this equation gives us that value. This is the total potential energy or external loads of the beam in this position, which is in equilibrium, and the equilibrium position is shown with dashed line. We have this one, which is given with equation 10. Just sum these terms with this term and you will obtain that one. According to statics, the order of loading does not change the result. This result can be a support, reaction force, or an internal force, or the potential energy of external forces. Okay. So here, as mentioned earlier, we applied all those P1, P2, P3 forces first, and then make an increment here in the magnitude of dP1 and obtain the result. But according to statics, if I applied P1 plus dP1 and P2, P3, those loads simultaneously, I should have obtained this value again. Nothing must have changed according to statics. Now, according to figure 4, this one, you see, now this is statically applied. The load is statically applied, so there is 1 over 2 in front of it. And the displacement in the direction of load is that one. Same things are done for P2, P3, and their corresponding displacements. And we obtain this equation. This is equation 11. As you will see, equation 10 and equation 11 are equal. Okay. So are equal to each other. The expression given, so they should be equal according to statics. That's why we set them equal to each other, and then from this new equation, they must have been equal to each other according to statics, and then I obtain this equation. Okay, after some amendments. And this is equation 12. Now replace equation 12 in equation 9 here. And I will get this one. Since these two terms both are differential or very small, it is neglected, and I get this value. And from this value, I obtain this value. And according to this value, the the derivative of first derivative of ud with respect to P1 gives me delta 1. So Castigliano theorem is true again. This was another way of proving that the Castigliano theorem is correct. But till that point, we will prove that Castigliano theorem is correct. But in this way, it cannot be used. Why? We have mentioned previously. In the formula, Castigliano theorem, this theorem cannot be used. Because UD shall be obtained depending on independent P's. There are deltas, displacements in UD. But all those deltas are not independent from each other or P forces. By this way, it cannot be applied. But what can we do? And actually, in the textbooks, they say Castigliano theorem is that one, but in numerical examples, they make different. Since the potential energy of external forces is equal to potential energy of internal forces, they use this formula always. In the subject theory, they thought that Castigliano theorem is that one, and it's true. But in the application of numerical examples, they apply this one. And clever people, engineers, confuses because the term they use in numerical examples is the potential energy of internal forces, not external forces. But we can do this because in statics we are dealing with conservative systems. Okay. However, ui must be a function conforming to deltas and be a function of pj only, not other p's. For example, if j is 2, ui shall not include p1, p3, p4, etc. Shall include functions of deltas and p. In the numerical example, we will see that. Now here we have a numerical example. UC, UI is the potential energy of internal forces. Actually, internal forces, these are internal moments. But you know, this term is much higher than the other terms coming from shear forces and normal forces, or shear displacements or shear deformations and normal forces, or let's say longitudinal axial elongation. How shall I say that? You know, the extension of this formula is as I remember, it was something like that. This is moment, this is shear force, this is normal force. Actually, this is m moment times curvature, and this is shear force times shear deformation, and this is normal force times axial deformation. Okay? But those two terms are very small in comparison to that one. That's why they are always neglected. To obtain the vertical deflection of a beam at its midpoint, given in figure 5, a concentrated load P having the zero value is applied to the beam's midpoint, as you see here. By this way, M moment function includes P. Okay, but its value is 0. And to take the first derivative, we need symbol, not a numerical value of p. We will put the numerical value of p later. As a result, ui includes p and the first derivative of the internal potential energy of internal forces can be calculated. Now you see, this is the this is our beam and loads acting on it. Reaction forces, this reaction force is 0 because of the symmetry. Vertical reaction forces equals to 1/2 of the total vertical load. And if I made a cut from here, and point x is anywhere here between this point and between this point, so x is between, point x is between 0 and L over 2. There is internal moment here, Q load. I don't need to show normal force and shear force here because I will take moment about point x, and they are passing from point x, so they will not enter, they will not be included in the moment equation. If I take the moment of all forces and this internal force, now it acts as if it is an external force on point x. If I write the moment equation about point x, I will get this one, and I will obtain the expression of moment. As you see here, it includes only p. It includes only p. Q, it's also load. They are independent from each other. And x, which is a variable. So it's suitable to use in this equation. Okay. Here we don't have any delta. We don't have any delta. We have all load values which are independent from each other, Q and P. So this is suitable. The first derivative of this function can be taken. Now, because of the symmetry, I calculate 2 times this value. Now you see I changed the boundary to the L over 2, 1/2 of the beam length, and multiply it by 2 because of the symmetry. If this part is multiplied by 2, it equals to the total internal potential energy of the beam. Internal potential energy is equal to potential energy of internal force is equal to potential energy of external force. Now this is equal to that one, you know, from mathematics. And if we do this, we have here 2 times 2 over 2 times EI. And here, if I apply this one, I will first take the first derivative of m square with respect to m, and then I will multiply it with this one. Okay? If we do this, we get 2m here, and this is so. And then continue. I know m function here. Okay? Here I have 2 times m, so 2 times this value, 2 times this value. And then the derivative of this function m with respect to p. If I take the derivative with respect to p, there is no p here. Here I have p times x over 2. So I will get x over 2. Okay, x over 2 here. Now you can put 0 instead of p, and then continue to calculate, to integrate, but you will get this result. This is the same result as the one given in the literature. So numerically, by using an example, numerical example, we also proved that the Castigliano's theorem is true. I prepared this document for myself and for other people who are experiencing confusing when they are reading textbooks, because in the theory, when they are teaching the theory in textbooks of strength of materials, even famous strength of material textbooks, they always mention that Castigliano theorem is so, but this is the potential energy of external forces. But when they show the solution, they use the internal potential energy of internal forces, because they have to do this so. Okay, because if they write the external potential energy functions, there would be deltas here, and okay, p forces are independent from each other, as q and p are independent from each other. When I take a derivative with respect to p, this term will be zero, because it does not include any p. But this term would be p over 2 times. From this term will something come, because it includes p from the derivative of its anything I will obtain. This is the okay, p, q are independent, but deltas develops because of external loads, p's, q's, external moments. Okay, that's why they are not independent. You shall obtain their functions in terms of external loads, and this is impossible. But when you write the potential energy of internal forces, you see here, m is a function of independent loads, and the curvature m over ei is also given here in terms of independent, which are independent from each other, external loads. So this can be applied. Okay. Actually, in the application, Castigliano theorem is that Castigliano theory is this one. Just to remove the confusion from engineers who are thinking like me, why did you say use this formula and did so when you are solving the numerical example? I made an explanation. The reason is this cannot be applied because deltas are not independent from external loads, but here the actually delta, a displacement or deformation, m over ei curvature, is obtained by means of external forces. So this can be applied to solve numerical problems. Please subscribe to my channel. I will put this document to my education website. You can find it. I will later put it. Please subscribe to my channel to support me. Thank you.